Hello, everyone. My name is Markus Heckler. I am going to present the work entitled Beamforming Assessment for Antenna Arrays Installed onto a Small Unmanned Aerial Vehicle. This work has been developed by Leonardo dos Santos, Liebert da Silva, Edson Schlosser, and myself in the Laboratory of Electromagnetics, Microwaves, and Antennas from Universidade Federal do Pampa in southern Brazil. The summary of our presentation is as follows. I will start with an introduction about the topic. Then I will show the aircraft model. Next, I will talk about installed performance of arrays of monopoles installed or on the wings, actually, of the aircraft. Then expose then the phase shifting circuits, which have been implemented with LC components in SMD format. Then we will, with these phase shiftings and the monopoles installed on the aircraft model, we will perform some beamforming assessment for 3 different cases of beam pointing, and finally I will present the conclusion of this work. One of the main reasons for developing this work was the in-flight safety and also for small aerial vehicles. These things are important for radio navigation system, which we designed to operate at 900 megahertz. Beamforming capabilities will be then demonstrated under this situation, and the frequency of 900 megahertz has been chosen in order to be a compromise in the size of the monopoles and the free space loss in the radio link. The aircraft model is shown here. So if we can, as we can see here, the wings are not covered, so only the structural part has been shown, as well as in the stabilizers here, the vertical and the horizontal stabilizers. In fact, this is a small unmanned aerial vehicle. This part here that has been removed, the cover of the wings, is actually made of a very thin plastic, so that in the frequency of design here, it is not relevant to include in the model. These parts shown in brown here are made of wood. These parts in blue are metallic ones, and the rest are also a kind of wood. So most of the aircraft is actually made of the electric materials, which is not commonly found in the literature, where we can mainly see aircraft composed of perfect conducting material. In our case, the wingspan is 1.8 meters, which in this frequency accounts for 5.6 lambda. And the length of the aircraft from the engine until the stabilizers at the rear part of the aircraft corresponds to 1.4 meters approximately, which corresponds to 4.4 lambda. This was a perspective view of the aircraft, where we can see most of the parts of it. So the engine is here. The propeller has also been removed because it is far away from the place where the antennas are actually installed. We can see here the monopoles. There are 2 arrays of monopoles. First array under the right wing, and the other array under the left wing, and the monopoles are numbered like this. So the 1, 2, 3, 4, 5, 6, and here we can see a closed view about these monopoles, where we can see then that we have below the wing ground plane, then the monopoles, and on the other side, it's not possible to see here, we have the microstrip feeding lines. Also, in the lateral part of the fuselage, we have placed a conducting plane so as to increase the isolation between this array and the array under the other wing. The performance of the arrays of monopoles has been done by using HFSS simulations. We extracted, using HFSS, we extracted the embedded patterns of each monopole so that we account for mutual coupling already from the beginning of the optimization. By doing so, every monopole has a unique radiation pattern so that the classical array theory, which stands that the total electric radiated electric field is composed of the radiation pattern of one isolated element multiplied by the array factor. This classical theory is not valid here anymore because of this fact. So we are trying then to produce three different beams. The first one is to the right, so the direction of the right wing, then in direction of the left wing, and in the front direction of phi equal 90 degrees. So here we can see then the aircraft here, and the radiation pattern resulting from these monopoles. So here we have for each antenna we have a different color, and we can see that each monopole has a unique radiation pattern, in fact. In order to achieve phase, to change the direction of the main beam inside an array, we have to change the phase of the elements, and this can be done in practice by using a kind of phase shifting circuit. In our case, we would like to use compact circuits for this, and we will use then pi and T topologies using RF components, along with RF switches as well. These topologies here are going to be used together with inductors and capacitors to synthesize transmission lines and to make the circuit compact and to be suitable for unmanned aerial vehicle applications. These are the two examples. So this is the pi configuration where we have two capacitors and one inductor. And here we have the T configuration also with two capacitors and one inductor. We could also have two inductors here and one capacitor, but we decided to minimize the number of inductors because of their quality factor. So it's more interesting, in our opinion, than to use two capacitors and one inductor only, and therefore the configurations that we will use are these ones. So the design of these structures, so the LS, CP, CS, and LP, are calculated by modeling or comparing, let's say, the ABCD matrix or transmission matrix of the pi configuration and the ABCD matrix of a transmission line, which would be needed to provide the needed phase shifting. Also, we do the same for the T configuration, and then the expressions are those here. So we have to compare then the transmission matrices, and then by the required beta L, so the phase shifting, we can adjust then the L and C components. So here we have then the solution of this problem. Here we have done modeling on the electromagnetic simulator. So here and here the SMA connectors, and then here is the pi configuration. So two capacitors and shunt capacitors and one series inductor. And here we have the T configuration. So two capacitors and one inductor here. So yellow here is the FR4 substrate, and these lines here are made of copper. Then we could achieve then the phase shifting, which are shown here, plus and minus 90, plus and minus 45, plus minus 22.5, plus minus 11.25 degrees. And then the needed calculated values for the components, inductor and capacitor. If we do that in the simulator, then we can see the phase shift that we can get. So our target frequency is 900 megahertz. So you can see here, this is for minus 90 phase shifter. This is for minus 45. This is minus 22.5, and this is minus 11.25. And this is for positive phase shifting. So we can see that at 900 megahertz, we can see that we got the needed or the desired phase shifting. Then for the beamforming assessment, we used particle swarm optimization. The main beam should be switched according to the orientation of the airplane so that a hangover can be made between the two arrays, hence making the communication stable with the ground station. For three cases here, in order to point the main beam to 95 degrees, to 135 degrees and 180 degrees, we can see that the desired or the optimized pattern with PSO and the simulated pattern already implemented in HFSS. So in the solid curves, we see that the fields that or the radiation pattern we can obtain with the embedded patterns already with the monopoles already installed in the aircraft, so that the whole optimization is done not only considering the monopoles but also the complete aircraft structure. So at the end of this talk, I can say that we managed to do full wave, an optimization by connecting it to a full wave electromagnetic simulation. So we could precisely perform beamforming, and the main beam could be successfully varied in the yaw plane, so in the horizontal plane, let's say, of the aircraft, and the gain was 8.2 dBi. So thank you very much for your attention.